I'll begin. Heavenly Father, we thank you for this day. We thank you for the break, which is about to start. I just pray you'd help us to focus in this time and just to accomplish something for your glory, Lord. In your name I pray. Amen. I'm fairly certain there's a typo in my next example I was about to cover. And so I decided what I'm going to do is go ahead and just jump ahead to my lecture 28. It's kind of a more coherent thought. I'll have to come back and pick up the pieces. Like the most important thing that I am skipping over at the moment in my notes would be the proof that if we take polynomials over a field and we take the quotient by an ideal generated by an irreducible polynomial, then that gives us a field. So that's an important construction that allows us to generate fields by quotients of polynomials, which is really neat. So I'll likely post a little video to pick up the piece that I'm missing here. And but in the interest of giving a more coherent thought, I think I'm going to go ahead and skip ahead to my lecture 28, which is, by the way, touching into chapter 5. All right. Now there are bits and pieces of chapter 4 I've missed at the moment, for sure. After the dust settles, we will have covered up through section 5.2. All right. There are bits and pieces of chapter 4 I've covered. There are bits I haven't. I'm going to take some time over break to try to figure out what exactly I still need to say to you guys to complete the story here. But just to let you know where we're going, I'll finish covering my lectures 28 and 29 in my notes from last year, and not today, and also up through section 5.2 in the book. That's where we'll get to this semester. All right. So here it is. This is my old lecture 28, as in 2016. Of course, this is not our lecture 28. It's actually our lecture, I don't know, 31, 32. I got to count. But here it is, definition. Let D be an integral domain. All right. And let A and B and D, elements of D. Then we have three things. Number one, A and B are associates if there exists a unit such that what? For which B is equal to AU. Okay, so associates are related by multiplication by a unit. Okay, so how about if you have a field? Pick two elements of a field. All right? Are they associates? A field's an integral domain, so we can ask the question, right? Yeah, not zero. Well, I guess if they're
One zero, you just multiply by zero.
Yeah, I think zero is associated to zero, but A and B doesn't. I mean, associate doesn't assume non-zero. Yes, everything in it, right? Because you can just say, well, B is equal to A inverse B, so this is a unit, right? I mean, there you go. And field's commutative, so you know. So this is not a particularly interesting idea in a field, is it? Okay. How about integers? What are the associates of 5 in the integers? Plus or minus 5, right? A is an irreducible. So notice we're now defining irreducible in a slightly different context than we did before. I mean, certainly polynomials are an integral domain. Polynomials over a field, that is. That's an integral domain, and that's where we defined irreducible before. But now I'm generalizing it to a arbitrary integral domain, right? And so here it is an irreducible if A is not a unit, all right? And whenever A is equal to CD, then either then C or D is a unit. Now, if you think about our definition of irreducible for the particular integral domain of polynomials over a field, this is going to be consistent with that usage, right? Because that's pretty much the same as saying, I mean, a polynomial can be factored into two. What are the units in f of x? They're just f, right? Non-zero f, the non-zero elements of the field. So if you think about it, this is consistent with our previous definition in that context. 3, A with A not equal to 0 is prime. All right? If A is not a unit and A divides BC implies that A divides B or A divides C. Okay? So I think for most of us, we were essentially taught that the definition of prime is irreducible. At least when I think about an integer, I think about what does it mean for an integer to be prime? What do you think? I think about 5 is prime because it has no factors except for what? 1 in itself. And if I was more honest, I would say it has no factors except for 1, minus 1 itself, and minus 5, right? Those are all there, right? Because 1 and minus 1 are the units there. But, you know, that's not the definition of prime, actually. That's the definition of irreducible. It just so happens that an integer is prime if and only if it's irreducible. So these terms of prime and irreducible are interchangeable for integers. One of the things we're after today is to try to get some sense of where these notions are distinct. Now this, I would say in the integers, we usually call this Euclid's lemma, right? Or, yeah, I think Euclid's lemma, isn't it? I believe that's its name. You know, for example, if 3 divides A times B, that implies that either 3 divides A or 3 divides B, right? 3 is prime. Yeah. All right, so what's an example of something? We obviously, you'd like to have an example which distinguishes between irreducible and prime, right? So here's an example of that. But well, I guess I'll follow my nose. This is example. I mean, there's a hole in this example which I fill in after it, and I guess we'll do the same in here. Example 3.62. We consider, and you've had a homework on this, but if we take z and adjoin root d, right, then that's equal to a plus b times the square root of d, right, such that a and b are integers. Here I'm assuming, of course, that d is what? Well, no, not that. Square free. D could be positive or negative. Weirdly, if it's negative, it's nicer. Strangely enough, but it's true. So in other words, D could be like 35, but it wouldn't be good for D to be 50, right? Okay, so in particular, we're going to look at D equals to minus 3. So we're going to consider, in particular, we're going to study 1 plus the square root of minus 3, which is an element of z, adjoin the square root of minus 3. Okay? And so, in fact, after this example, I'll show next that 1 plus the square root of minus 3 is irreducible. All right? That's not obvious, I think. And we need that construction of a norm that you guys have the homework exercise, problem 21 about. We're going to use your problem 21 where you built up this function which is multiplicative and so forth, had all those nice properties, remember? We'll use that to show it's irreducible in a minute. But for now, I want to show you that it's not prime. Okay, so, so check this out. We have 1 plus the square root of minus 3, right, times 1 minus the square root of minus 3. What's that give us? Right, so yeah, 1 minus a minus 3, which is 4, which we could also write as 2 times 2, right? So what does this show? What does this show? I'm missing something here, guys. I say thus, maybe you can help me out. I can't spell thus, not a good sign. Thus, excuse me, 1 plus the square root of minus 3 divides 2 times 2. Is that? I don't see how I get that. Oh, sorry. I'm a victim of my own grammar. Yes? I don't think I've actually shown that yet, is the point. Suppose you could. I think we're going to reach a contradiction, all right? So suppose, I'm sorry, guys. Let's try to solve 1 plus the square root of minus 3, all right, times a plus b times the square root of minus 3 equals to 2. Suppose you could find a and b integers such that we had that.
So we're assuming it's prime. I'm trying to get this
Yeah. Well, is that what we're doing?
We're trying to that if no such A and B exists, then it can't possibly be prime, because otherwise it would divide 2. Because I think that's what you're after.
Our definition of prime is that if we have a divides b, then b times c, then either a divides b or a divides c.
Well, B and C are 2 and 2 in this case, so.
B and c are 2 and 2.
Because I think from this we see that 1 plus the square root of minus 3 does divide 2 times 2. We want to show it doesn't divide 2. Because that will contradict it being prime. I think that's what we're trying to do.
Yeah, we're trying to show that, we are trying to show that 1 plus root square root of minus 3 is not prime. That is my goal, which I am very painfully slowly reaching. So sorry. What's the idea of this? I mean, what's the...
What you wrote first was right, because you have 1 plus the square root of negative 3 times some
Yeah.
equals 2 times 2, so that's the definition of divides.
Divides
So,
4?
It divides 2
Yeah.
times 2, which is B.
which we just broke up into 2 times 2.
But why would that say it? I'm sorry, I'm just an idiot. Why would that say it divides 2? I understand
No,
what.
it divides 2 times 2.
Oh, okay.
Yeah.
If it's prime, it will divide 2, and we're going to show that it doesn't.
So we know that it divides B times C, which is 2 times 2. And now to show it's prime, we have to show that it
Right.
has to divide both.
Oh, okay. I'm sorry. Sadness. Anyway, forging ahead. This is good. I mean, the point of this lecture is for you guys to try to learn the definition of associate, irreducible, and prime. I mean, that is our main goal today. So if my poor exposition helps you in that direction, great. So let's see here. This is A minus 3B, right? And then plus what? Plus, what we got? A plus B times root 3? Root minus 3, rather, equals to 2. Do we agree? So what does this give us? This then gives us two equations. On the one hand, we have a minus 3b equals to take a look at this. It's dangerous for me to say anything today. A minus 3b is 2, and a, what is this? A plus b should be 0, right? So we're trying to solve the integer equation what? So this just that gives us minus 4b is equal to 2. So that says that b is equal to minus a half, which is hard to do, right? These equations can be solved over the rational numbers, and we find that the solution is in fact not existent in Z, right? So there's no such A and B. Consequently, let's see here. So how does that show, again guys, help me out here. How does that prove that 1 plus the square root of minus 3 is not prime? Because 1 plus the square root of minus 3 divides 2 times 2, but 1 plus the square root of minus 3 does not divide 2, right? Very good. I need to be explicit. There remains the question, how do I know that, 1 plus the root, how do I know that 1 plus the square root of minus 3 is irreducible, right? And so that, we use a theorem, which is your homework problem, which is that, and this is more generally true, if D is square free, all right, and we define the norm of a plus b squared d as equal to the absolute value of a squared minus db squared, all right, for each a plus b squared of d in z adjoin root d, right? Then we have some very wonderful properties of this, and this is called a norm usually in like number theory and such. And I understand that terminology is at odds with our use of the term norm in linear algebra. It's unfortunate, but the word norm is used in multiple ways in different parts of math. The only two I've actually seen, though, are pretty much this one and the one you see in linear. In its many ways, it's used. But a norm in number theory is some integer valued, it has to be positive integer valued function from your whatever you're looking at, and I think it has to satisfy the multiplicative property I'm about to write down, and this also. I mean, anyway, so I'm not trying to define a norm in general. We pretty much are just interested in this one at the moment anyway. So n of x is equal to 0 if and only if x is equal to 0, right? 2, the norm of xy is equal to the norm of x times the norm of y. And this is, of course, for all x and y in z adjoin root d. And 3 is really nice, which is that x in z adjoin root d is a unit, right? If and only if what? If and only if the norm of x is equal to 1. This is really neat. This means if you want to find the units in z adjoin root d, all you got to do is solve the equation absolute value of a squared minus db squared equals to 1. All the solutions to that are your units. That's it. For example, well, how's this, well, this is cheating. But I mean, that actually is, if you think about what the norm would be for the, I mean, this is extending the concept a bit, but if you'll just allow me this comment. What would the norm be for the integers? What's the norm of an integer?
Absolute value.
Yeah, just absolute value, right? And if you set the absolute value of x equals to 1, what do you get? Yeah, and those are the units in the integers. That's not an accident. And I think if you look at these 4 properties, it would also be satisfied by absolute value on the integers. So this, in some sense, is generalizing that notion of absolute value to these, what are called algebraic numbers. Well, I'm not saying that this is a case of this. I'm just saying this is like it. But I don't think it actually is a case of this. I think you're right. It's not. Well, but it would definitely be problematic because these would definitely not be like the fundamental thing about these kind of objects is that if we have a plus b root d equals to a prime plus b prime root d, we want to be able to separately say a is equal to a prime and b is equal to b prime. D equals 1. It's not going to go well for us. If n of x is prime, remember n of x is an integer, right? In fact, it's a positive integer. Well, it's non-negative, I should say. If n of x is prime, then x is irreducible. Right, now I think you had in your homework, I believe you guys have done 1, 2, and 3, right? I think. I don't think you've done that yet, have you? No, so we should try to prove 4. So I think the proof is just a contradiction proof, right? Suppose, well, I'll try a direct proof, why not? Suppose, I don't know what I'm going to write something down and see what happens. Suppose n of x is prime. Let's suppose it equals p, a prime. And suppose that x is equal to ab, where what? Neither a nor b are units, right? That would say what? That I'm saying x is not irreducible, which is a really clumsy way of saying it's not reducible. In other words, x is reducible. Yeah. Anyway, so then you take the norm, right? The norm of x is the norm of AB, right? Which by the property you guys did prove in your homework is the norm of A times the norm of B, where by 3, neither n of A nor n of B is what? Is 1. Oh no, we just factored a prime. This is bad, right? Consequently, if n of x is prime, x is irreducible. Do you see why this is such a nice tool for these these objects, this particular ring, z adjoin root d? It's because we trade these kind of complicated questions about a plus b root d for just a simple question about an integer, right? Applying that to my previous example here, to see that this is irreducible, it's a simple matter of calculating the norm. What's the norm of 1 plus square root of minus 3? Absolute value of what? 1 squared. What am I supposed to do? Plus, so plus 3. And then when my b was, my b is 1, wasn't it? So that's 4. Huh. What?
Wait, is it d squared or b squared?
I'm sorry?
Is that db squared or is it just d times b squared?
D times b squared, I believe.
Yeah, because oh, never mind, because it's root d. That does turn to. Yeah, no, it's fine.
There's no biconditional, is that this is just one of the cases where the test fails or what?
Oh, it's a little bit more subtle than that. It's not just, I mean, there are cases where you can apply it directly, okay? There's still a little bit more logic to see why that's irreducible. So let's suppose it reduces. We got a little bit further to go. So suppose, I'm sorry guys, I wish it was that simple. It's not quite that simple. Suppose this is equal to x times y, right? We're getting there. In other words, suppose it was reducible, right? Then we feed that to the norm. Then the norm of 1 plus the square root of minus 3 is equal to the norm of x times the norm of y, right? And this is what? Well, we just worked that out. So we get 4, right, is equal to the norm of x times the norm of y. Then what? So keep in mind that n of x and n of y are integers, right? And they're not 1. If they're 1, we don't care. We're interested in non-unit factorizations of this, right? So we're assuming that n of x and n of y are not equal to 1. Which is just a quick way of saying that there are not units. Do you guys know what the units are in this thing? I don't know if we've ever even listed those, right? You don't even know what the units are, do you? I mean, that's fine. I can tell you 2 of them. 1 and minus 1. There you go. And say I didn't do anything for you. There are probably others. But let's focus. We don't even need to know that. That's the beauty of the norm. We don't even need to know that, what the units actually are. All we need to know is that we don't need norm 1 here, which means that this has to be what and what? How can you get 4? This implies that n of x equals to n of y equals to 2, right? That's the only way we can get 4 from the product of 2 whole numbers, not 1. Neither of them being 1. You can't do minus 2 times minus 2 because the norm is well, whatever you want to say. It's in my usual language, the natural number is union 0. Or Nicholson would just say n. So sorry. Okay, so then what? So we can try to let x equals to a plus b times the square root of minus 3, right? And we can try to see, can we find the norm of that, right? Can we find that equals to 2? Which is to say, can we solve the equation a squared minus 3b squared equals to 2? Does that have any solutions?
Would that be plus?
Yes. Thank you. So you can start plugging in things, right? So your best hope is b is equal to 0 in some sense, right? But b, if you put b equals to 0, then we can't solve a squared equals to 2, right? So you have fine. I'll put b equals to 1. You put b equals to 1, all of a sudden you got a 3 here, or plus or minus 1 even. And so you can't do it.
A and B are integers.
Yeah, a and b have to be integers.
We could just mod 3, right? And then b squared equals 2. 0 doesn't work. 1 doesn't work.
Ah, very good.
2 doesn't work.
So you're like, so you're thinking reduce mod, what do you say, mod 3 is how you see there are no solutions. Very good, very good. I just say this one is simple enough. I think I can just manhandle it with direct integer logic, but reduction mod of prime is even better.
Okay, mod 3, when you get a squared plus b squared equals 2, which means you just let a equal.
Well, mod 3 would just be a squared equals to 2.
Oh, duh. Yeah.
Three terms of 0. So, sorry.
So that would be, I'm not sure there are no solutions to a squared equals to 2 mod 3?
Well, 0, 1, and 2, and those are 0,
Zeros.
1, and 1.
Okay, then no, yeah. Good. So anyway, the point is, yay. So tracking this back, this shows that there is no element with norm 2 in this number field. This set of, these are usually called algebraic numbers or something like that. There is no such element. Consequently, there's no way to factor this, right? Which is to say that that's irreducible. And yet, it's not prime.
We didn't use part 4. Like, we got the norm of x. Oh, so it just, part 4 just failed because the norm of x wasn't prime, so we couldn't use it all.
Yeah, we couldn't use it directly here. I've got an example I can show you where we do use it. Just give me a second. My current speed, we won't finish until Christmas. We don't have class in Christmas, right? Just checking. It seems like, our finals end like when? Like December, what is it? 19th? I think grades are due the 22nd or some such thing. I don't know. If you give somebody an extension in an online class, all of a sudden you're working through Christmas. It's like, I don't know. He's not good. Any of you guys go to the game? Obligatory. Come on. Come back to me. All right. Let's see here. Ah! The stupid computer turned itself off yesterday, and with it, it closed all my PDFs. No, no, no. All right, so the one we just worked through was example 3.66. We worked through that in some detail, I think. I hope you understood what we did. Here's one, I think, where we used part 4 directly, Sam. Although this one's actually a little bit harder. But it's worth a look. So let's look at it. If I can find my laser. Oh, got no laser. My laser out of batteries anyway. I'll use more traditional methods. Let's see here. All right. So here we're going to look at z adjoin root 5. And for z adjoin root 5, we can look at 7 and ask the question, is 7 irreducible in z adjoin root 5, right? Suppose it was. Well, the norm of 7 is 49, right? And so how can you get 49 as a product of two numbers which are not 1? You have to have 7 and 7, right? So the question then is, can we find a plus b root 7, root 5? 5. Sorry, I'm very annoyed by that. That's supposed to be a 5. Such that 7 is equal to this, right? In other words, can we solve a squared minus 5b squared equal to plus or minus 7, right? Now, so if we think about this, any integer solution of this is a solution of that equal to 0. There's a 0 missing here, so sorry. Right? We're using your idea now, Alan. Reduction mod 7, right? And so if you explicitly check out the solutions, there are 7 of them. The only solution is actually a and b, both 0. Actually, that's not honest. How many solutions are there for a and b in mod 7? 49. Yeah. There's about 40 cases to check here. But the only thing that works out is 0, 0. Okay, so there's a little bit of detail missing in what's typed here. But rest assured that 0, 0 is the only solution there. And so what that means then is that 7 divides A and 7 divides B. Okay? And yet, which would suggest that this is divisible by 49, but it can't be equal to 7 and be divisible by 49. So no such A and B exist. Consequently, 7 is irreducible in z adjoin root 5.
Thank you.
I think it works if you mod 5 also.
You mod 5, it works directly?
Yeah.
That's
You get a squared equals 2.
But the 8 are you working mod 5?
huh.
4. Yeah,
Huh. So mod 5. That's funny. See, I got this argument out of Gaussian, and his point here might have been to illustrate a calculational technique, not to, although it may not have been a necessary calculational technique, as you are, I think, finding. It's good. This is very good. So what is good is that you're thinking for yourself, and that I like. So I like that a lot. In an integral domain, every prime is an irreducible. All right? Here's the argument. Suppose A is prime, right? If A is equal to xy, then since A is prime, that means either A divides x or A divides y. I shouldn't say either or. I don't mean either or. I mean mathematical or, right? Could divide both. It's possible. So anyway, suppose A divides x. Then that means that x is equal to AB, right? So look at this. X is equal to x times, well, x is x times 1, right? But we also know x is equal to AB, right? And but we can expand A into x times y, right? Which then gives us x times yb. But then we've got x times 1 equals x times yb. We're in an integral domain where we have cancellation. So that gives us that 1 is equal to yb. Which means the only way you can have 1 equal to yb is if y is a unit, right? So in the context that A divides x, that proves that the other one's a unit, right? Which means it's not irreducible. But A was, you know, there's nothing special about x here. X and Y is commutative. If you can prove it for X, you can prove to make the same argument for Y. So by symmetry, the same argument works if A divides Y. So any way you slice it, A equals to XY implies either X or Y is a unit, which is to say that A is irreducible. You can't find a non-associate decomposition of it. Like if you form a decomposition of it, that means either X or Y is an associate of A. See, because either the one that's remaining is a unit, which is going back to say that they're associates. Of course, this concept of associates is really important, and it'll help us a lot with explicit calculations going forward. We're trying to find the representatives of a factor ring. This is very, very useful. And the fact is that if you have a commutative ring with identity, or in other words, for us, if we have a ring, if A and B are associates, then the principal ideal generated by A is equal to the principal ideal generated by B. Furthermore, if R is an integral domain and I is equal to the principal ideal generated by A, then any other generator of that ideal is an associate of A. So if you want to find, in the context of a ring, if you're looking at an ideal, if you want to find all possible generators for a given ideal, you find one, and then you find the units for the ring, and multiplying by those units, your given generator, you will obtain all known associates of the generator, which are all possible generators for that ideal. This is wonderful. This is very simple. I mean, there's still something that has to be done, like what are the units in this one we talked about a second ago? Like what is this actually? What are the units in here? What do you got to solve what? You got to solve A squared. Is it minus? I can't remember. Plus 3B squared, is it? Equals to 1? Right. So what are the solutions to that? I already got the easy ones. A equals to plus or minus 1, right? Are there any others? Oh, and I keep forgetting, well, I was like, I'm forgetting my absolute value, but that's actually okay here, isn't it? This absolute value is really most interesting when D is what? Positive, yeah.
So D being negative kind of makes it more easy to work through, I guess.
D being negative gives a certain finiteness to it. Like when D is positive, there are infinitely many units. For example, if D equals 2, you'd have A squared minus 2B squared equals to 1. Anything in there would be a unit. Gives you a unit A plus B root 2 in Z adjoin root 2. Then there are infinitely many solutions to that. Is this Pell's equation? You number theory people? Nah, never mind. Oh, fine. Okay, anyway, here it is. Getting back to my proof. So suppose A and B are associates, all right? That means there's a unit such that A is equal to BU. In other words, B is equal to AU inverse. If we suppose that X is an element of the ideal generated by A, that means that X is equal to AR, right? But of course, you can trade your A for BU, and then you get X is equal to BUR. Of course, UR is in the ring, which means that X is an element of the ideal generated by B, right? So I've just showed that an arbitrary element in here is in there, which is to say that the ideal generated by A is a subset of the ideal generated by B. And you can reverse this argument to show that, of course, B is a subset of A, which gives you then that A is equal to B. The ideal generated by A is equal to the principal ideal generated by B. And then, of course, it remains to show that all of the generators are associates, right? So that's just all I've shown so far is that associates generate the same principal ideal. Let's suppose that C generates A for some other C in the ring. Our goal is to show that C is an associate of A, right? So if A is just the zero ideal, then A is equal to 0, right? And I think what I really want there is to say what? I think I want to say that C is equal to 0 here. I guess not. I'm sorry. I'm majoring in the minors here. I'm explaining to you why, if this is equal to 0, it must be that A is equal to 0. This is kind of a giant duh. A is not equal to 0 implies that A times 1 is equal to A, which would say that A is in there, which means that all I'm really saying here is A is in the principal ideal generated by A. So if the only thing in the principal ideal is 0, A must be 0, right? Anyway, if you didn't have this sentence in your proof, I probably wouldn't notice, is my point. What I'm saying here is if A is equal to 0, then clearly that forces C to be 0 as well, all right? So suppose A is not equal to 0, all right? If A is not equal to 0, that means that C is also going to be not equal to 0, since the ideal generated by A is equal to the ideal generated by C by assumption. We have that A and C are elements of this, and we also have that A and C are elements of that, right? So you can find S and R in the ring such that A is equal to RC and C is equal to SA. And so then we can play the cancellation game again. So we have A is equal to RC, but I'll trade my RC for, what do I do here? Oh, I trade my C for SA. And then, what do I got? Oh, and then I could write A as like 1 times A, right? And then that would give me that RS is equal to 1, right? I didn't actually write that down, but I said it in words. So this implies then that RS has to be equal to 1 by the fact that we're working in an integral domain. Consequently, R is a unit, which shows that A and C are associates. There's a lot of words here, but this is a legitimate test question, right? I mean, you look at every step of the way here, these are not difficult things to come up with. Even if you haven't memorized this proof, and this is exactly the kind of proof I would say you mustn't try to memorize. You absolutely must understand this proof for yourself. Write out a proof for yourself for this one. You know what I mean? That'd be wise. I guess we never answered my question. Is there any other solutions to this? No?
B non-zero. Any kind of B non-zero is going to give you 3b squared at least 3.
So that's it.
Yeah.
Cool. Of course, this is the Gaussian integers, right? What are the units in the Gaussian integers? We're looking for a squared plus b squared equals to 1, right?
So one of those is 0 and the other is
Right. So we have a equals to plus or minus 1, b is 0, or we have a is equal to 0, and b is equal to plus or minus 1. In other words, you got yourself a 1, a minus 1, an I, and a minus I. Yeah, the 4th roots of unity are the units of the Gaussian integers. I can tell you for certain that those are the only units of the Gaussian integers because those are the only ones that have norm 1. Of course, you could find that directly, but it's nice to have it as part of a larger story, right? In a principal domain, an element is prime if and only if it's irreducible. We just proved one of the directions here. We just proved that prime implies irreducible, right? Conversely, suppose that A is irreducible, all right? And we want to show it's prime. So suppose A divides B times C. For some B and C in the domain, we define this ideal, which is AX plus BY. You can prove that this is an ideal. I do that down here, all right? In particular, I take the difference of elements and show that it's such an element. I take the product of something in the domain, multiply it by such an element, I show it's again there. So I is an ideal, right? Now, so what? Well, we're in a principal ideal domain. I think I may have buried that. So if this is an ideal, it's principal. That means that this I can be written as angle bracket some element. There's the generator of it that gets the whole thing. So since D is a PID, we know I is principal. That means there exists a D such that I is equal to that. But we have that A is equal to A times 1 plus B times 0. So A is in this ideal, right? Consequently, A is equal to R times D, which shows what? That shows that, well, like I said, since A is irreducible, we have what? We have R or D is a unit. What does that give us? Well, if D is a unit, that means that 1 is equal to DD prime. Yeah, and that would make the ideal the whole ring. So I can get 1 from some linear combination of x and y, multiply by c, and I get this. So naturally, A divides ACX. Yeah. We assume that A divides BC. So by this equation, we have what? If A divides this, A divides that, that means A divides C, which shows what? That's what we're after. We assume that A divides B times C. We wanted to show that either divides B or C. And we showed that it divides C.
Well, that's only if D is a unit. We didn't address it. Oh, no, you do underneath that.
Yeah. On the other hand, if D is, what is this? If R is a unit, on the other hand, then we get A is equal to RD, which proves that our A and R are associates. And then we have that that this ideal is that ideal, which is to say that B is equal to we can get B in the ideal, and that means that B is A times lambda, which means that that A divides B. So either A divides C or A divides B. Those different cases correspond to whether or not the generator of the ideal is a unit or not. So sorry I had to go through this a little bit fast, but you should, please take the time to work through this for yourself. This is like one of those pretty important proofs that I should have spent more time on today. I'm sorry I didn't, but at some point or another, the break has to start. Let it begin.